Hey everyone, today we're going to be talking about speed and velocity and how that speed and velocity is going to relate to the motion of objects, how we can describe the motion of objects, and how we can calculate speed and velocity given different distance and displacement and time information. So we'll start by looking at speed and kind of relate the difference between speed and velocity, which we talked a little bit about in class today. But speed, which we represent with v, because it is representing the same magnitude when we talk about the velocity, so they're going to use the same variable v. So the speed, or v, of an object is the distance that the object moves in a unit of time. And as we learned in class today, or talked about, speed is a scalar quantity, meaning it only has magnitude. You can refer to the speed of somebody without describing what direction they're headed in. The average speed, which we designate by v bar, it's got the little bar above the top here, so that's going to constitute average speed of an object, is given by the equation d over t, where we measure the distance, or we'll learn it can also be displacement. It's measured in meters, our standard unit, and time interval measured in seconds. So our unit becomes, since we have d over t, it's going to be meters per second. Or we represent that as a fraction, m over s. And this is a derived SI unit. Meter being the standard and seconds being the standard for distance and time respectively. So if an object's speed is constant during the entire time interval that we're calculating our velocity, or calculating our speed, the object is said to be what we call a uniform motion. Meaning that the motion, if we were to graph it, looks consistent. We don't see something that is speeding up and slowing down. And when we translate this over into graphs, that'll make a little bit more sense. This is going to give us a constant slope. If we're talking about an object where the speed is not constant, then our object is not going to be in uniform motion. Our graph is not going to be completely linear. If the speed of the object varies, the motion is non-uniform. Now the velocity of the object is the time rate of change of the object's displacement. Velocity is a vector quantity. This is what separates it from speed, which means it has both magnitude and direction. So if we were to just think about the magnitude of an object's velocity, well, magnitude of velocity without direction, so we consider the scalar portion of the unit, well, that's actually just the speed. Once we add a direction to speed, it becomes velocity. If we remove the direction from velocity, it becomes speed. So for example, if a car is traveling 85 kilometers per hour headed east, and a second car is traveling 85 kilometers per hour due south, both of these cars are traveling with the same speed. But even though they have the same speed, both the cars have different velocities. And that's for one main reason. Get this here. And that's because the one car is headed south and the one car is headed east. Because of the different direction, so because the direction is not the same, the velocity is going to be different. Even though the speed is the same, the direction is different. So if our direction changes, our velocity is going to change, even if the speed does not. Velocity and speed cannot be used interchangeably. Linear motion, if you think of linear, your experience with the word linear, linear motion refers to an object's change of position along a straight line. And that's where our linear comes in. Along a straight line. On a straight path, there's really only two possible directions for velocity. We might want to call it left or right, or forwards or backwards. But we're going to call it the positive direction which would make the opposite direction of the positive direction the negative direction. Depending on the direction of the motion, changes in the displacement are also going to be positive or negative. So we use the symbol V, as we discussed earlier, to represent velocity, and it's also going to be representing the speed. It's going to depend if we actually have a direction on it or not. The symbol D can be used for displacement and distance. Depends which one we're referring to. What amount of information do we have to include in that quantity? So to give you an idea here about how we look at motion, we're going to look at the moving man. So this moving man is currently placed at a starting point here of a distance of 0 meters. So we can kind of call this the origin. We see a negative scale to the left and a positive scale to the right. So if I wanted to put my person to the right, I would want to put him at the positive 4 value on the x-axis. He moves to the right. If I call that a negative 4, he's going to move to the negative 4 value on the left. I'm going to include the velocity vector here so you can see this. If I give him a velocity of 2 meters per second, the positive direction is to the right, so his velocity should be pointing towards the right. If I give him a bigger velocity, we should see that equivalent change in the arrow. Remember, vector arrows are drawn to scale, and I might not always use them to scale in class, but on these simulators and when you guys are doing calculations or problems or doing scale drawings, they should be to scale. If I give him a negative velocity, again, negative just means in this case here, to the left. He should get a velocity to the left. And again, if we increase that velocity, the arrow should get bigger. If we set him in motion here, with a positive velocity of 1 meter per second in the right direction, and we hit play here, he's going to move with a constant velocity in the positive direction. And we can use his change in position or his displacement over the time to calculate his speed. This can be done over a period of time. This can be done instantaneously. So negative direction, we could have flipped these two. Negative could be to the right, positive could be to the left. It all depends how the user defines that. Graphs of linear motion. We're going to focus on these during class. So graphs of distance versus time are commonly used to show the linear motion of an object. And they're going to produce a pretty standard type graph that you're going to have to be able to not only understand, but be able to convert those graphs into velocity over time and then into acceleration over time. But when we use graphs of linear motion, we always represent time, which is our independent variable, on the horizontal axis, which is where our independent variable goes, on the x. Which means the dependent variable, what we're recording, is the position. That'll go on the y. So since average velocity equals this distance divided by the time, the magnitude of the slope, so how steep or shallow the slope is of a distance versus time graph, at any point equals the object speed at that instant. And the algebraic sign of the slope is going to indicate, let's retry that one there, it's going to indicate whether the velocity is in the positive or negative direction. So depending on how we look at that slope, is it positively or negatively placed, it's going to tell us the direction in which that object happens to be moving. And again, that's simply just going to be correlated to a direction, left, right, forwards, backwards, but they're always opposite of each other. A graph of linear motion that has a straight line is going to indicate constant velocity. When we see these linear lines, they're going to indicate that whatever the value happens to be, whatever the variable happens to be, it's going to be constant. The slope is the same, which means the rate of change over time is the same. A straight horizontal line represents zero velocity, meaning that the object is at rest. If we do find a distance versus time graph that is curved, then we know that the velocity is not constant. And if we were to find the slope of a line that's tangent to that curve, where the velocity is not constant, so at any point there along that curve, if we draw a tangent to that, let's say we were to have a curved line here, if we were to draw a tangent line at any point here, the slope that we have is going to tell us our instantaneous velocity at that moment. So this is the instantaneous velocity. So the tangent to a curve at any point on the curve is defined as, and this should hopefully be review, the line passing through the point of interest and having a slope of the curve at that point. And again, that's just kind of represented here, where this red would be our velocity. So to define the instantaneous velocity, It is the velocity of an object at any particular point in time. That term is applied to the motion of an object that's not traveling at constant velocity. Otherwise, we would have a constant velocity. We wouldn't have to calculate instantaneous because it is always the same. Well, the steeper the slope of a distance versus time graph, the greater the instantaneous speed. Now we'll do some translations of this in class, but so you guys can see this, let's actually pull up the chart so you can see this here. See if we hit play here. This guy's not going to move anywhere. He does not have a velocity. So let's give him we'll start him at a position of 0, and let's give him a velocity of 1 meter per second in the positive direction. Let's see what that does to his position here. We have 3 different graphs, and we're going to start translating between these 3 over the next several days. But let's look at his position. He's going to move in the positive direction, so we should see a change here along the y-axis in the positive direction. So let's see what that looks like. Let me adjust that here. We'll give him 1. There we go. And let's see his change in position. So that's a constant velocity. We see the increasing positive slope there as he moves away from his starting position. We'll stop him at about 3 meters displaced from his origin. And we're going to give him a velocity of -1. He's now going to move back in the opposite direction. We should see a change here on our y-axis back towards the origin. And it should be straight because this is a constant velocity. Once he reaches back to that 0 point, he is back to the origin. We can stop him there, and he's now returned back to his spot. We'll see how we translate position versus time to velocity versus time. And then you can see here how we'll take velocity versus time and translate it into acceleration versus time. We'll do our next video on some practice with calculating speed and velocity of objects using different information. For now, I'll leave you with a joke. Who was the name of the first electricity detective? It was Sherlock Holmes. Have a great day, everyone.